I, Somesh, welcome you all on behalf of Group A3, which is working on Arduino-based temperature sensor to the phase 3 submission video, which is primarily based on benchmark results. First things first, the objective of our project is to control the surface temperature of a thermoelectric cooler using an Arduino-based temperature sensor. In this video, we'll be covering the following topics. There's a brief overview and showing of the circuit diagram, which is used for implementing the code and actually controlling surface temperature. We'll then take you through the explanation of our code, which we have implemented in Arduino IDE and how that works. The major part of the code is the PID control algorithm. We'll explain you the theory and how exactly does the PID control algorithm, the value of 3I and D, are used in our experiment, in our setup. We'll then show you the benchmark results, which will involve the experiment running video, all the graphs including of the error and how temperature goes up and comes to the same temperature values. Along the way of the implementation, we face several challenges and how actually were those troubleshooted is also included in this phase of the video. Moving ahead, we have planned some innovations. Some innovations we have already implemented. Some are planned for over the next 7 to 10 days, which we'll be implementing. Those are considered the bonus experiments. And in the end, last but not the least, the future plans, which we have, including the report and the bonus, the implementation of the bonus experiments.
Thank you so much. Now we are going to discuss the setup of our project. Here you can see in the picture, this is the peltier with heatsink. Here both the negative positive ion of heatsink and peltier we attach together because we want to on and off the peltier heatsink at the same time. Because if we start the peltier, then lower side of temperature will decrease, go down, then we need to dissipate the temperature. Therefore, we want to on the heatsink. Now, negative or positive wire of heatsink and peltier we are connected with motor driver, and at the same time, negative wire and positive wire of the power source we are connected with the motor driver. And now coming to the temperature sensor, here temperature sense we have attached the upper side of the pins. While we attach the upper side of pin, it will explain by my friend later. Here temperature sensor and motor driver is connected with the Arduino. Arduino provides a power supply to the both. If I on and off the peltier, then temperature will go up and down. This temperature sensed by the temperature sensor, and here temperature sensor senses the temperature and forward the data to Arduino. Here Arduino we have done some code which will decide the peltier will on or off. Then Arduino will give the message to motor driver. The motor driver will control the power supply.
Now coming on to the temperature sensor. So we'll use a thermistor in this setup. A thermistor is a type of resistor whose resistance is reliant on temperature. So it's basically a resistance thermometer. The most commonly used is the NTC, the negative temperature coefficient thermistor, and it is the one that we have used in our setup. So the NTC's resistance decreases as the temperature increases, and vice versa. With varying resistance, the amount of current flowing through the resistor changes the temperature, and with this change, it is possible to correlate between the current and the temperature of the resistor. NTC thermistors can be adjusted incrementally with their operational range, and they can maintain great accuracy. Due to significant variations in the resistance per degree Celsius, small temperature changes reflect properly. They are precise when used within a limited temperature range, that is within 50 degrees Celsius of the target temperature, and this range is dependent on the base resistance. Thermistors are also nonlinear, that is, the connection between the resistance and the temperature won't always be a straight line. It will form a curve on the graph. When the line sits at how much it changes, it depends on the thermistor and how it is made. So now coming on to the setup, we initially used the thermistor and adjusted it near the bottom of the peltier, which is too close to the base plate, which is at high temperature than the peltier. And due to this, the radiation from the base plate affects the reading taken by the temperature sensor. So this causes some error in the readings. So then we try to adjust the temperature sensor on the top surface of the peltier. But due to the round tip of the sensing, the round sensing tip of the temperature sensor, it was not in proper contact with the peltier surface. So at last we adjusted the temperature sensor in such a manner as shown in the figure, as it is slightly adjusted between two fins of the peltier. Now the assumptions made in this setup were that due to the short length of the fins, the temperature along the fins of the peltier does not change, and that the temperature is almost the same across the fins of the peltier.
Now let's look on the coding part. So initially we have tested the relay using this code in which we have set the baseline temperature, and based on the condition we have set the relay out. So here we have defined the baseline temperature and defined the relay pin to be in 10 in Arduino and as the thermistor pin in in-out. In while setup we set in-out pin is to be input and relay to be out, because in-out pin taking input from the temperature sensor and relay is giving output to the further device. As the procedure of the loop, initially we are taking analog input from the sensor, then print the temperature to the serial monitor in Celsius and Fahrenheit, as we can see from here. Then we put the condition that if the current temperature will be lower than the baseline temperature, then the relay will be on. So here we are using digital value, so that the relay will be turned on and off using 0 and 1. The another condition is if the current temperature will be equal to and greater than the baseline temperature, then the relay will be on. So that is why we have set the relay comma 0 here. So this is how we have tested the relay with our system. Now coming to the code in which we have implemented the control algorithm to control the surface temperature. The flow of the code is as follows. So initially we have defined all the variables like dt, set temp, min temp, maximum temp, and set time. So here dt is the time in between two outputs which are coming from the motor driver. Set temp is the temperature which we want to achieve at the end of the experiment. So here we have used the PID control algorithm in which we have used the concept of range. So for that we need to define its minimum and maximum limit. That is why we have defined these two variables. Here we have set the set temp with 20 degrees Celsius. For that we have decided to be set min temp is 17 degrees Celsius and maximum temp is 23 degrees Celsius. Here the set time is a time for which we need to run the system. Here we have defined the pins for taking inputs and giving output. So the thermistor pin is the analog pin from where the temperature sensor taking inputs. The relay pin which is connected to the 10 number pin in the Arduino. So now we have used the PID controller algorithm. So for that we need to define its three gain, AP, KI, and gain. So here we have defined this. Now we have imported the Arduino math library math.h that includes a number of useful mathematical functions for manipulating floating point numbers. Some other variables, as we can see here, be in range and x per ms. We have defined this. Also for PID we have initially assumed the previous error to be 0. Now the code part of this code is this control PID function, which will be explained in detail later. Conventional way, in void setup we have defined the set relay as output. Now the procedure is followed as per the command are written in void loop section. So first the temperature sensor is taking the analog input from the surface, and then the temperature goes into this PID control PID function, and it being controlled as per the algorithm. As we can see here, these lines of code are making sure that after the setting time over, the output of the relay will be low and the controller stops.
So this is the block diagram of our control circuit. Now let's look at the few terms involved in here. Basic term. The process variable is the actual value, the value that we are measuring. In our case, is the measured value of the temperature. The set point is whatever value, say 20 degrees Celsius or 15 degrees Celsius we have set. Error is the difference between the set point and the process variable. Set point minus the process variable is the error function here. Now why a PID controller? PID controller, we are trying to answer two basic questions here, that how much is the correction to be applied and how quickly is that correction to be applied. So the two questions, how much of the correction in magnitude to be applied and how quickly is that to be applied. For that we use the PID controller, and this block diagram, this unit is the PID controller. which takes in the error and gives it, modifies it, adds some gains and integral, and then gives it so that we can get a desired response more closer to the set point value, the process variable. Now the first part of the PID control algorithm is the proportional algorithm. So as you can see, its value is Kp into the error function. This tells us that farther the system is from the set point value, the larger the gain from the Kp would be. So say our set point is 20 degrees Celsius and we start somewhere at 35 degrees Celsius, the temperature in the air that we have. So the farther we are from the set point, the more the value of this contribution from the proportional algorithm would be. So we can tune Kp in such a value so that the fast we reach to the set point values. The next is the integral algorithm. Integral algorithm has its some inherent advantages. You can see that it not only takes the magnitude of error into account, but also the duration for which the error exists. So Ki will keep on contributing to the error as long as the error exists in the system. To put it in one sentence, Ki is just used to reduce the steady state error of the system. So say this was the set point and the system reaches near the set point, so if there is some steady state error, the Ki what we would try to do is it try to reduces the error which exists at the steady state. The next is the derivative algorithm. It is quite interesting here that the derivative algorithm having dE by dt, the rate of change of the error part, actually gives it the ability to look into the future, what the error would be in future. And so for our case, our practical application, we try to keep the KD value in control, because the temperature sensor, the NTC thermistor that we are using, what it actually does is it actually takes in a lot of values and gives output at one point, not continuously give values, but collects values and give it at one time. So the dE by dt value would be a large value in this case, and we have tried to control we have tried to put a smaller value of d so that it does not actually overpower the proportional and integral values, the contribution of the proportional and integral values. So this is the application of the PID algorithm to our particular project. Over to the next speaker.
So now let's take a look at the results that we are getting on running this code. The temperature variable in the serial monitor indicates the current temperature that is being observed by the temperature sensor, which in this case is 35.55 degrees Celsius, which is near about the room temperature. Now let's start running the code. In the code, the set temperature is 20 degrees Celsius. We have also set two other variables, which is the max limit and the min limit. If the temperature observed by the temperature sensor is greater than max limit, which in this case the max limit is 23 degrees Celsius, so if the temperature observed is greater than max limit, then it will instruct the thermoelectric cooler to run at the full speed. And if the temperature observed is less than min limit, then it will instruct the thermoelectric cooler to completely stop. Since right now it is above 23 degrees Celsius, so as we can see, the cooler is running at the max limit. Since now the temperature falls inside the margin of max limit and the min limit, so PID control algorithm start working. We have manually tuned the PID control algorithm in this case. The value of Kp is 200, Kd is 10, Ki is 0.01. Now 17.6 is the value that we are observing, is also called the percentage overshoot, which is the amplitude of the first trough. And now the PID control algorithm is oscillating back and forth with the set temperature. By changing the propeller speed of the Peltier, it is trying to bring the temperature observed at the surface close to the set temperature by reducing the error by oscillating back and forth. In this case, the Kp, Ki and Kd that we are seeing on the screen are basically the contributions of proportionate, integrated and derivative term of the PID control algorithm. Since we have manually tuned this PID algorithm, so we will not get exact, that is the zero error, but we can further improve the temperature that we are getting by using more advanced control algorithms or more advanced tuning method like tuning using MATLAB Simulink, or by using other hyperparameter tuning algorithms. In this case, the nearest value that we are getting is 20.17 and 19.08. That is, the lowest error observed by us is positive 1.7 and negative 0.2. And as we move more along time, this is the error that we'll keep on observing.
So now let's take a look at the plot. The plot in this case is between temperature and the time, and error and the time. So as you can see here, the error is the difference between the observed temperature and the set temperature. And as we move forward in time, the error keeps on reducing. So initially the error was near about 10, and as we move ahead, the error keeps on reducing, and the minimum error that we have observed, which is this, is 0.17 and this is 0.2. So these were the two minimum errors that we were able to observe here. The observed temperature line, when the first time it goes beyond the set temperature, is called the percentage overshoot. So here we are observing percentage overshoot, and as we can see that since we have manually tuned it, so there is certain residual error which is left at the end, but we can overcome this error by doing better tuning using advanced algorithms. The key point that we can note from here is that since we have manually tuned it, the error keeps on oscillating, and eventually it will reach where the residual error will be minimum after a long duration of time.
Now let us come to the point where we did some troubleshooting in our first complete experiment, thus making some changes from the initial. So we came from relay to the motor driver in our goal set. So we use the relay module at first, which is a kind of electromagnetic switch which helps us to control a big power circuit using a small power signal, which is received from the Arduino in our case. Digital write function is used for the relay module, so we can either switch on or off and cannot control the fan speed. But we face some challenges while executing the experiment using the relay module. The signal's frequency, that is the switching on and off of the relay, affected the temperature sensor reading. Thus, the temperature sensor gave us a random reading along with the actual Peltier surface temperature. To cater to this issue, we replaced the relay module with a motor driver. The main advantage of the motor driver over a relay is that it provides a PWM signal, which stands for pulse width modulation, as the motor in general requires a PWM signal. This feature also helps us provide an analog write using a digital pin on Arduino board. Hence, temperature sensor could work smoothly with the reading temperature in real time with proper accuracy. Also, the Peltier rating is 92 watt and with 12 volt supply from SM base. Thus, we need around 7.67 amperes of current, and the motor driver, which is rated at 30 volt and 10 amperes, which is apt for the Peltier rating. Apart from that above mentioned challenge, we also could even remove the sound disturbance from the relay. Now, for the future aspect of the project, we have the following modifications. So, for modifying PID algorithm, there are some features through which we can tune the PID algorithm to make it more robust for the setup. Three of them, which I have mentioned over here, are the MATLAB auto tuning, root locus hyperparameter tuning algorithm. And for bonus experiment, we have the humidity sensor. As you can see, even I have included a photograph of ES311 sensor, and which helps us to sense the humidity as well as the temperature. Along with that, we would also like to observe what is the effect of heat sink on the Peltier.
Yes, so implemented the control algorithm, implemented PID, all the setup and done. We are able to control the value, bring it to a range where the temperature stays within some bounds around the set temperature, which was 20 degrees Celsius for our case. Now let us see how much is this valid and transferable to the real world scenario, the real world applications we face. We all have been in situations where we run these many applications on our laptops, hundreds of Chrome tabs running, we forget to close all of them, and our laptops gets hotter. We see that our laptops have fans, they have coolers, they have the devices there, but it does not actually always bring it to the optimal level, and the laptops do get hot. The another limitation that we see is the current temperatures here in Gandhinagar and the area around 35 to 37 degrees Celsius does not exceed that value. And say if it was very harsh summers and the temperature values are high, and we perform the experiments in sunshine out, and we cannot predict whether our experiment, our control strategy, our devices will be able to sustain those conditions and actually bring the temperature to lower values around 5 degrees Celsius or 10 degrees Celsius. So yes, implemented the control strategy, the algorithms, but still these are some of the practical limitations that are associated with our project, which we would like to work upon further if possible.